Hi everyone, as you can see we are looking at exponential graphs in this video. So this is taking our work on indices and looking at what it looks like in a graph form, I suppose. Now it should be pointed out that this is the first of a couple of videos exploring exponential graphs. In this video I will go through what exponential graphs are in general, and then in the next video we'll look at transformations of exponential graphs. Okay, so let's see how we go. Now, let's have a look at the basic form of an exponential graph. It's not to be confused with a power graph or a power function where you've got y equals x to the power of something. In an exponential graph, uh, we've got y. Let's just choose y is equal to some base to the power of the variable x. So y equals a to the power of x. And what we need to do is try and figure out, well, what that graph looks like. You can sort of use the usual approaches that you would to other graphs, I suppose, and that's just have a look at different values of x and see what would happen to the function. So, for example, you can look at intercepts. You can look at when x is positive and when x is negative. And look at what happens when x is a fraction as well is probably useful. I guess the word exponential, though, is really important here because I don't know if you're used to seeing the word exponential in a general English way, but when something is said to be growing exponentially, it means that over time it gets bigger and bigger and bigger, faster and faster and faster. So maybe if you can visualize what that might look like as a graph, you'll know where we're headed here. Okay, so I have to say that the graph will change depending on what the base is there, or what a is. So let's keep that in mind, but let's just assume a is some random positive number just to keep it nice and simple. Then let's have a look at what happens when we explore what's happening with x. What's happening to y when we change the value of x? So I guess the simplest thing to look at would be when x equals 0, right? Which would be the y-intercept. Yeah. So remember that when we're graphing things, y-intercept. The y-intercept is when x equals 0, and the x-intercept is when y equals 0. We've done that with so many functions. That still continues, I suppose. Well, what happens when x is equal to 0 here? Okay, we would have y equal to a to the power of 0, which is equal to 1. So in an exponential graph, in your basic form at least, it's gonna the y when x equals 0, y equals 1, which is that point there on the graph. Okay. Then what happens when x gets bigger? Just on a basic level, as x gets bigger, y, which is the whole of a to the power of x, is going to get massively bigger, I suppose. So we're going to get this kind of form happening. Okay, it's not meant to be a parabola. It's meant to be a line that's increasing quickly. And what about when x is getting bigger but negative? Well, when I have a value like a to the power of negative n, remember that our indices laws tell us that that's equal to 1 on a to the power of n. In other words, a negative power turns a value into a fraction. So it doesn't turn the value negative, it just makes it a fraction. So on the left-hand side, what we have is it getting smaller and smaller and smaller. I better just extend that line. And smaller and smaller and smaller. Okay, it's approaching 0, but it never reaches 0. There's no value of x that I can put in, positive or negative, that will give me the value 0. It's just that as x gets bigger in a negative sense, then it becomes a to the power of x becomes a really small fraction. Okay, but it never hits 0. And as x gets bigger in a positive sense, then obviously it just skyrockets up. Okay, and then the swing point, I suppose if you want to call it a swing point, is when x is equal to 0 and we have a y-intercept of 1. Okay, let's have a look at that in Desmos, because that will graph it nice and prettily for me. Not that my graphs aren't pretty, yeah, they're not pretty, but here we go. Ah, there we go. Thank you, Desmos, for being so pretty. So you can see that this is y equals a to the power of x. That's the y-intercept when x equals 0, y is equal to 1. And then it climbs steadily that way, and it declines steadily that way, getting closer and closer to 0, but never getting there. If I zoom out, you can sort of see how steep that graph gets when we get x equal to 50 and keeps on getting. So that is just a hallmark of an exponential graph. It's just a steep incline. And then after 1, we can see that there's, I've got as far as negative 150. It hasn't crossed over, and it never will for the reasons I said before. Okay, so I'll just zoom in again. There we go. So that's our exponential graph in its basic form. But what I thought we might do is just explore perhaps what happens when we change that base value. So what you see here, I'll just go back to Desmos again, is y equals a to the power of x, where a is 1.6. I just chose just a random number above 1. Okay, so let's have a look at what happens when a is above 1. What happens to the graph? As we increase a, what's happening? It's hopefully obvious. The bigger the value a is, the steeper the graph will climb. Obviously, if I'm raising 2 to the power of x, then that's going to be climbing nice and steadily and quickly. But if I have 2 to the power of 10, for example, 2 to the power of 10, where is it? Oh, it's just off. It's way up there somewhere. 2 to the power of 3, then 2 to the power of 3 will be there, okay, at 8. But if I now make it 10 to the power of 3, that same value at 3 is off the chart again. It's because it's at thousands, and 10 cubed is 1,000. So the bigger the value of a, the steeper it is. Okay, but basically the basic shape of the graph is that. I'll draw that in. So if I'm sketching it, I will simply draw my axes. Use a ruler, not like me. X and Y. Put my y-intercept of 1. There is no x-intercept because it gets close to 0 but never gets there. And then I'm just putting my iPad on its side so I can draw this, but I'm sort of just drawing through 1. It's probably better if you draw the line first and then say where 1 is, to be honest, unlike what I've done there. I'd even put an arrow on the end, even on both ends would be good, like so. So that's the sketch of y equals a to the power of x when a is greater than 1. All right, the next thing is looking at when a is between 0 and 1. Maybe you should pause for a second and think about what you think the graph might look like. Okay, so I'm just giving you a chance to pause the video and maybe just do a quick sketch yourself. When a is between 0 and 1, a is a fraction. What will that do to the graph? Do a quick sketch. Okay, if you've had it, hopefully you've had a chance to do that. Let's use Desmos to see it in action, and then we'll just do a quick sketch. So I'm just going to use the little slider action here to get below 1. Did you get that? When a is a fraction, then it has the effect of flipping the graph. Notice that it still goes through 1. That should make sense to you, I hope. It goes through 1 because a fraction to the power of 0 is still 1. So it still goes through 1. But because it's a fraction, when I raise a fraction to a big power, then I'm going to just get a very small number, hence it's approaching 0. When I raise a fraction to a negative power, then I'm going to get a very big number, and hence it's increasing below 0. Remember, this is the power effectively here. What doesn't change is the base. Okay, this is 0.6. So when a is a fraction, we have just the opposite basically. So it goes down and goes towards 0. That's y, that's x, and this is still 1. Okay, so why does that work? Well, indice laws again, I suppose. Index law, which goes 1 on a to the power of negative n is equal to a to the power of positive n. So when x is negative, the negative power here makes the number itself bigger for y. And when x is positive, we just have 1 on a to the power of n, I suppose, that law, which simply means that as n gets large here, it's a 1 over a big number, and as that number on the bottom gets bigger, it gets closer and closer and closer to 0 without actually touching 0. Okay, so that's the two main things to look at when you're looking at an exponential graph. Let's just cover the other bases as well. What happens when a is less than 0? We'll click over to here. Let's go down to 0 past it. Oh dear. Oh dear. It's not there. Okay. It's not a well-defined function when a is less than 0 because of what the effect of powers has on negative numbers. Okay, it doesn't create a well-behaved graph. Okay, so that's handy. Why? Because oops, we can just say not applicable. Really, if a is less, so a isn't. You won't come across graphs that you'll need to create where a is less than 0, which is nice. And two other quick examples. It's almost not worth mentioning, but I might just ask you to think about it. Okay, what happens when a is equal to 0? What's the graph going to look like? Give you a chance to think. Pause if you need to. Okay, let's have a look at it. So going to positive there, down to 0.2, down to 0.1, down to 0. You can actually see there is a line there. So it's not defined for negative numbers, and then suddenly it's defined for 0 onward. So you can sort of, as long as you restrict the domain, then you're okay. Okay, so, but it's a bit trivial, it's a bit useless, so we probably don't need to really worry about it too much. Okay, so it's trivial. Don't worry. So when you see the word trivial in maths, it just means it's so not useful, it's not worth exploring further. Okay. And the last one there is y equals a to the power of x when a equals 1. Wonder what that would look like. Getting flatter and flatter. Oh, there we go. Unsurprisingly, when a equals 1, the graph is just a straight line because 1 to the power of anything is just 1. Okay, so it's trivial as well. The value there is 1. Y, x, trivial. So yes, if you were given that function, in a test, you'd say you beauty because it would be so easy to do, but you won't. So effectively, you'll only be given problems where a is positive and not equal to 1, basically. So when it's positive and greater than 1, you have the graph looking like this one here. Oops, a daisy. That was a bad move. Press the erase button instead of the draw button, the point button. When a is bigger than 1, you've got this graph, and when a is a fraction greater than 0, then you've got this graph here, so the reverse of the graph. Always cutting through 1. Of course, there are transformations that we can apply to this to make it shift around the place, but we'll deal with that in the next video. Last thing I just thought I might touch upon is domain and range. Let's have a look at the function again, giving it a reasonable value like that. Okay, so remember domain are possible values for x. So are there any values for which the function is not defined? No. I can have negative powers, I can have 0, I can have positive powers, I can have fraction powers, decimal powers. So there's no restrictions on the domain. But there is a restriction on the range. Remember the range is the possible y values. So what are the possible y values? Well, pretty much anything up above in these quadrants, isn't it, really? There's some values. The graph is along here. The graph is along here. But there is no graph in these quadrants here. So what does that mean? It means that y can be positive. Can y be equal to 0? I don't think so. So what's the domain then? So the domain, I'll just use my fancy little chord cursive stuff for the domain. So domain, sorry, yep, got it up there. Domain is equal to all possible values of x such that x is a real number. Okay, it's enough this year to simply go x is all values of x, something like that if you want to. If you want to put it as an interval, you can say x is a member of negative infinity to infinity if you prefer. That's fine as well. That's an interval, so that's interval notation, set notation, okay? Range is all values of y such that y is a member of the real set and that y is greater than 0, not greater than or equal to, but greater than 0. Or if you prefer interval notation, y is a member of 0 to infinity, like so. Do note that you need to use the round brackets here for 0 to ensure that they know that 0 is not included in the range. You'd use square brackets to say inclusive and 0 to say it's not inclusive. And we always use a round bracket when we're dealing with infinities because infinity is weird. Okay, one last thing I'll say, then I promise I'll stop. Looking back at the graph there, we have kept on talking about the fact, well, I have anyway, that the graph approaches 0 but never reaches it. Whenever you sort of hear that language of approaching a value but not reaching it, you should be thinking about limits. And in terms of graphing, you should be thinking about asymptotes. So in this case, there is an asymptote, a horizontal asymptote at y equals 0. That is a horizontal asymptote. So that idea of asymptotes will be explored a little bit further in the next video when we look at transformations on an exponential graph. But I think that will do for now.